the sum n equals 2 to infinity, n minus 4 over n squared minus 2n plus 1. So let's let f of x equal x minus 4 over x squared minus 2x plus 1. This function is continuous as long as x does not equal 1. Notice that x squared minus 2x plus 1 is x minus 1 squared. So the only time this denominator is undefined is when x equals 1. We don't have to worry about that because n is starting at 2. All right, is this thing positive? Well, it's actually not positive at every single term, but it is positive for n greater than 4. The denominator is always positive. I should say x there. I'm sorry. We're talking about the function f of x. Okay. The denominator is always positive because it's the square of x minus 1, but x minus 4 is only positive when x is greater than 4. Well, that's actually good enough. Okay. As long as it's positive from some point on, that's good enough. And the same thing for decreasing. So this is one of those examples where showing that it's decreasing is actually a little bit of a pain. All right, not as simple as the last example. So I think that the most common way to show that these functions are decreasing is to do what we did back in Calc 1, which is to show that its first derivative is negative. Okay, so let's look at the first derivative. F prime of x. Using the quotient rule, the first derivative of this function is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. All right. So if we pretty this up a little bit, I'm going to FOIL those two binomials, x minus 4 times 2x minus 2, and that's going to give me 2x squared minus 10x plus 8. All right, and then simplifying the numerator, I get negative x squared, and then minus 2x plus 10x is plus 8x, minus 1 minus 8 is minus 9. Okay, so the question about this is it negative or is it eventually negative? Well, yes, it is, because if you factor a negative 1 out of the numerator, that gives you x squared minus 8x. No, this is not going to work out as nicely as I thought. Okay, so I'm not going to be that exact about it. I'm just going to say that this thing is definitely eventually negative. I was hoping it would factor into something nice, but I don't think it does. Because at some point that negative x squared is going to overpower the rest of the numerator, plus 8x minus 9. Okay, so as long as it's eventually negative, that means that the function is eventually decreasing, and that's good enough. Okay, all right, so we have shown that the series in question is going to have the same behavior as the improper integral 2 to infinity of x minus 4 over x squared minus 2x plus 1. Okay. Now I'm just thinking about how I want to do this. Let's see. Well, I'm going to do the same thing I did before. I'm going to get my antiderivative first. Oh, I guess I'll be super official about it. Okay. This is a partial fractions integral. Do you see that? So I think we can just skip right to x minus 4 over, and remember this is x minus 1 squared. So that means there are some mystery numbers a and b such that x minus 4 over x minus 1 squared is equal to a over x minus 1 plus b over x minus 1 squared. If you multiply both sides by the LCD, you get x minus 4 equals a times x minus 1 plus b. And now I'm going to plug in x equals 1 to get one of those values. It's going to give me -3 is equal to a times 0 plus b, which means b is -3. I'm all out of good numbers that will make either a or b drop out. So whenever that happens, I usually go to x equals 0 if I haven't used it already. And that's going to give me -4 is equal to -a plus b. But we know that b is -3. So if we add 3 to both sides, we get -1 is equal to -a, and that means a is 1. All right. So now, unfortunately, I only left 2 screens for this problem, which is not enough. So I am going to go back now and get rid of this. The important thing is that b is -3 and a is 1. Okay, so that means we're going to rewrite this integral as integral 2 to infinity of 1 over x minus 1 minus 3 over x minus 1 squared. Okay, writing that integral as a limit. I said I was going to find the antiderivative first, but actually now that we've got it written in this form, this antiderivative will be very easy. 1 over x minus 1 minus 3 over x minus 1 squared. All right. Antiderivative for 1 over x minus 1 is natural log absolute value x minus 1. And then if you think of that second term as -3 times x minus 1 to the -2, by the backwards power rule, that antiderivative will be plus 3 over x minus 1. Plug in b, plug in 2. So we get limit as b approaches infinity, natural log, we don't really need this absolute value. Everything's positive. Plus 3 over b minus 1 minus natural log of 2 minus 1, which is natural log 1, that's 0, plus 3 over 1, which is 3. Okay, well, there is just one thing here that's going to kind of spoil the whole thing, and that's natural log b minus 1. As b increases without bound, so does natural log b minus 1. So this limit is actually infinite. And so remember, the integral test says that the series and the integral will do the same thing. We have just shown that this integral diverges. Therefore, by the integral test, the series n equals 2 to infinity n minus 4 over n squared minus 2n plus 1 also diverges. And I can't wait until we get to, I believe it's the very next section. You will see a much easier way to show that this series diverges. All right. All right, so now we come to example 2. This is the one that had the instructions that said just figure out whether the series converges or diverges, and it doesn't tell you how. I'm still going to do this one by the integral test. You will get a better sense of this after we've seen a couple of more tests. There's really 2 more sort of major ones coming up. But whenever you see that the series, the general term of the series, can be turned into a function that you know how to integrate, that's kind of a clue that it might be integral test. And by the way, once we have our complete bag of tricks, integral test will always be sort of a last resort, because if some other test works, it will probably work more easily and more quickly than the integral test. All right. So please feel free to try other tests before you use integral test. Once you know some other tests, you don't know very many yet. Okay, so once again, we're going to let, and I don't say this often enough, please, whenever I come to, you know, an additional example, and you think it might be something that you know how to do, please pause the video and try it. You'll get much more out of that than just sitting there listening to me do it. All right, question number 1, is this continuous? Well, yes, it is, as long as x is not 0, which it won't be, because again, we're starting the series at n equals 2. Is it positive? Well, we know the square root of x is always positive. Natural log of x is positive as long as x is greater than 1, which it is because n is starting at 2. Okay, so now we come to the always the most difficult question, is the function decreasing? So once again, I'm going to look at the first derivative using the quotient rule. That first derivative is going to be the bottom times the derivative of the top. So I'm multiplying by 1 over x minus the top times the derivative of the bottom. What is the derivative of the square root of x? It's 1/2 x to the negative 1/2, which is 1 over 2 square root of x. All over the denominator squared, which is just x, right? Okay, so let's clean this thing up. I'm going to multiply the top and the bottom by an LCD that will cover all of those little fractions. So I'm going to use 2x. Okay, so in the first term, the x's are going to cancel and will just leave me with 2 square root of x. In the second term, the 2's will cancel and I can divide square root of x into x and get square root of x. So this is going to be x, square root of x times natural log x. And on the bottom, I'm going to have 2x squared. All right, and again, the question is this first derivative negative, or is it at least eventually negative? And to see that, I'm going to factor square root of x out of the top. That's going to leave me with 2 minus natural log x. All right, so let's think about this. 2x squared is always positive. Square root of x is always positive. So as long as I can convince you that 2 minus natural log x is eventually negative, that will do it. Well, it is. It's negative as long as natural log x is greater than 2, which will happen whenever x is greater than e squared. In other words, yes, f prime of x is eventually decreasing. and that's good enough. Okay, so that means that we can look at the integral 2 to infinity of natural log x over the square root of x dx. All right, so for this one, I am going to get my antiderivative first. Start thinking about what integration technique would you use to get an antiderivative for natural log x over the square root of x? Well, I think I would use integration by parts. Integration by parts. Okay, so think of this as natural log x times x to the negative 1/2. Natural log x is a logarithm. X to the negative 1/2 is not technically a polynomial, but it acts like one. That means that u gets to be natural log x. dv will be x to the negative 1/2 dx. That means that du will be 1 over x dx. And v will be the integral of x to the negative 1/2, which is x to the 1/2 divided by 1/2. So it'll be that, right? Okay, so by ultraviolet voodoo, this integral is equal to 2 square root of x natural log x minus the integral v du. 2x to the 1/2 divided by x would be 2x to the negative 1/2. All right, so by backwards power rule, the integral of x to the negative 1/2 is again 2x to the 1/2. So that would be minus 4x to the 1/2 plus c. All right, we're almost there. So now what I'll do is I'll just keep my antiderivative at the bottom here. And I will write my limit for the improper integral. This is the limit as b approaches infinity. Integral 2 to b, natural log x over the square root of x dx. And we just found that antiderivative, so let's go ahead and plug that in. All right, let's see. So this is going to be 2 square root of x, natural log x, minus 4 square root of x. Plug in b, plug in 2. All right, so we have limit as b approaches infinity, 2 square root of b, natural log b, minus 4 square root of b, minus 2 square root of 2, natural log 2. I know this part's going to be a constant. I don't even really care about that part. What I really want to know is this limit infinity or not? All right, that's kind of the only important question. And it's kind of a difficult question, at least if you have it written like this. So again, I'm not worried about this part. This is just a constant. As b goes off to infinity, this term goes off to infinity, but so does this term. So what we have here is an infinity minus infinity. Remember, that's indeterminate. But I think if we rewrite this in a different way, I'm going to rewrite it by factoring. I'm going to factor out 2 square root of b out of only these two terms. If I factor out 2 square root of b, inside I'm going to have natural log b minus 2. And then again, we don't really care about this part. You know what? I'm just going to call this number. Okay, now once it's written in that form, as b increases without bounds, so does this, and so does this. Infinity times infinity is not an indeterminate form, it is infinity. So this limit is infinite, and therefore by the integral test, the series n equals 2 to infinity, natural log n over the square root of n diverges. All right, and that brings us to our last example, which I think you're going to like. The sum n equals 1 to infinity of n times the tangent of 1 over n. I am going to try something different on this one than the integral test. For one thing, I'm not sure I know how to integrate f of x equals x times the tangent of 1 over x. I'm actually going to try something we haven't really used very much. I am going to try the nth term test. I love the nth term test when it works. When it works, it's great. When it doesn't work, well, it's not so great. But it usually never takes a huge amount of time to try it. So again, this is the thing. Let me remind you what the nth term test says. It says that if the limit as n approaches infinity of a sub n is not 0, in other words, it comes out to something other than 0 or doesn't come out to anything, the limit doesn't exist or it's infinite or whatever, then the series diverges. Okay. When I go to use the nth term test and the limit is 0, then I feel a little disappointed because I didn't learn anything about the whether the series converges or not. Okay, so let's look at limit as n approaches infinity, n times the tangent of 1 over n. As n increases without bound, this goes to infinity, and this goes to tangent of 0, which is 0. So that's an infinity times 0. That is an indeterminate form. So let's rewrite that as tangent 1 over n divided by 1 over n. And then as n increases without bound, the tangent of 1 over n is going to 0, and so is 1 over n. So now that is a 0 over 0. Okay, now I remember showing this to you once before. I don't remember which section it was in. To make this just a tiny bit easier, I'm going to do a little substitution. If I substitute u for 1 over n, I can make this limit tangent u over u. And now I just have to think about, okay, limit as u approaches what? Well, if n is approaching infinity, then 1 over n is approaching 0 from the right. So that's what I have to put for u. U is approaching 0 from the right. By the way, this is actually a Calc 1 limit. I do not have to use L'Hopital's rule on this, but I'll go ahead and do it anyway. So by L'Hopital's rule, that limit is going to be equal to the limit as u approaches 0 from the right of secant squared u over 1, which is secant squared 0, which is 1. And what's the most exciting thing about 1 in this problem? The most exciting thing about 1 in this problem is that it is not 0. Hooray! So that means the nth term test works for this problem. And I can conclude that this series diverges by the nth term test. The series n equals 1 to infinity, n times tangent 1 over n diverges. And that's going to do it for section 10.3. We'll see you next time.